Okay, we're on to question number 4, and in question number 4, the first part gives you, it says, the sine of a is 1 over square root of 10, and it says, find the sine of 2a, and you also need to find the cos of 2a, and you give your answer in the form p over q, where you have two natural numbers. So your form is some fraction, no decimals, no square roots or anything like that. So, the way of doing these is like this. So you know from trigonometric ratios that if you have the sine of a is equal to something like this, well, you know from your trig ratios that you have sine is equal to opposite over hypotenuse. Something you know from the junior cert. So therefore, if we construct a right angle triangle and put the angle A, doesn't matter where we put it, this is telling us that 1 must be the opposite side and square root of 10 must be the hypotenuse. To actually fill this in, I can do something like this. Now, why would I do that? Well, I need to find the sine of 2a. We normally look at an identity in the logbook for the double angle formulas. It's in a page of your logbook where it gives you an identity for sine of 2a, where it says sine of 2a can be changed to 2 times sine of a times cos of a. Now, I have sine of a, but I don't have cos of a. But if I construct this right angle triangle, I do have cos of a because we know cos is equal to, from our trig ratios, adjacent over hypotenuse. Now, of course, we don't have the adjacent for a, we don't have that, but from Pythagoras' theorem we can get that because simply that's square root of 10, which is hypotenuse squared, is equal to 1 squared plus, let's call that x squared. Square root of 10 squared, well, that's just 10, is equal to 1 plus x squared. That means x squared, when that 1 comes over, is equal to 9. And we must be positive, so x is equal to square root of 9, which is 3. So therefore, we can definitively say this side down here is 3. Now, it's pretty easy because we know sine of a is 1 over root 10. But now we know this would imply that the cos of a is equal to adjacent over hypotenuse, which is 3 over root 10. So this is something we can use. Now, when we're looking for sine of 2a, its sine of 2a is equal to 2 times sine of a, which we were given as 1 over square root of 10. Cos of a, which we now know from our trig ratios, is 3 over square root of 10. Like so. So when we change all these and multiply them in, well, fraction is top by top, bottom by bottom. So essentially we have 2 times. 1 times 3, that's 3. Root 10 by root 10, that's like root 10 squared, which is just 10. And of course, 2 times 3 over 10, well, that's 6 over 10, which simplifies to 3 over 5. So, there's the first part done. Similarly, we have to find the cos of 2a. So again, I went to the logbook for double angle formulas and says an identity for cos of 2a is cos of 2a is equal to cos squared a minus sine squared a. Now, something that you must know is to say cos squared a is the same as cos a all to be squared, which is like cos a times cos a. So this is literally cos a multiplied by itself, and this is sine a multiplied by itself. So from that we can say that the cos of 2a, so what we're looking for is cos a by cos a, which is cos squared a, so cos a is 3 over root 10, so that's 3 over root 10 times 3 over root 10 minus sine squared a, so the sine of a was 1 over root 10 times 1 over root 10. Now, 3 by 3 is 9, root 10 by root 10 is 10, minus, that's just 1 by 1, over 10. So 9 tenths minus 1 tenth leaves me with 8 tenths, and of course that simplifies to 4 over 5. So that's the first part done. Now, in the next part it says, by expressing the sine of 3a as sine of 2a plus a, which of course 2a plus a is 3a, that's why they're asking to do that. It says, can you find the sine of 3a? So this is a compound angle type problem, sine of something plus something. So for this, we look at the construction for compound angle formula for sine of a plus b. So it gives an identity of sine of a plus b is equal to sine a cos b plus cos a sine b. So when you look at something like this, we have some stuff A, some stuff B. But of course, what we have our A matches up with our 2A here, and our B matches up with our A singular here. So what we can do is we can actually change this using this identity, but instead of using A, we're using 2A, and instead of using B, we're using A. So that would mean that the sine of 2A plus A now is equal to, so sine of A, that's the sine of the first stuff, which is 2A here. Then cos of B, that's cos of the second stuff, which of course for us is A. So that's cos of A. Plus now cos of A, which is cos of the first stuff. So that's cos of 2A for us. And then sine of B, which is sine of the second stuff, which is B for us. So remember from the first part of the question, we actually figured out all these things. We figured out sine A, cos A, sine 2A, cos 2A. So sine of 2A, what's that? Sine of 2A, that's 3/5. Cos of A, that is 3 over root 10. Plus cos of 2A, that's 4/5. And the sine of A, that's 1 over root 10. Okay, so we have 3 times 3, that's 9 over 5 root 10, plus 4 times 1, 4, also over 5 root 10. And of course, 9, these both have the same denominator, so we can bring them together. So 9 plus 4 is 13, and that's all over 5 root 10. So that's actually our answer there then. And it does say to give your answer in the form, something like that, A root B, it says, over C. So this is something that we have to be careful of. Normally we would be finished here, but of course that doesn't look like that. So how can we change this to something A root B over C, where all these are natural numbers in here? Well, remember, we can always change something, like in complex numbers where you multiply by the complex conjugate. We can change the look of this, much like we can change 1/2. We can multiply that by 4 over 4, say. That'd be 4 times 1, 4 times 2 is 8. Look, it's 4 over 8. It's still a half. It just looks different. So what we're going to multiply by here? Well, let's try the denominator. So say 13 over 5 root 10. Let's multiply that by 5 root 10 over 5 root 10. Okay? Now, of course, something over itself is 1. So by multiplying something by 1, remember, you're not changing what it is. A half and 4/8 are the same thing. Multiplying by this, it's going to retain the same numerical properties. It's just going to look a little bit different, right? So 5 times 13, that's 65, and that's root 10 on the top. And of course on the bottom now we have this stuff. So that's 5 by 5 is 25. Root 10 by root 10 is just a regular 10. So we get 65 root 10 over what looks to be 250. And we can cancel down this some bit. Obviously 5 goes into both of them. And actually, as I look at it, I could just multiply by root 10 over root 10, but however. So 5 into both, 5 goes into 65, of course, 13 times. And 5 goes into 25, 250, 50 times. So yeah, look, it's the same thing, it just looks a little different. It's just been a little bit awkward on you here. And of course, I didn't need to multiply by 5 root 10. I could have just said this part here, and it would have given me this answer straight away. But of course, I looked at it a bit too quickly. But there we go. That's it anyway. So in this last part, it says, gives you an equation that looks like this: 2 cos squared x plus 3 sine x minus 3 is equal to 0. And it says then, it gives you a big hint: express as a quadratic in sine x and solve for x, where x is going to be a value in radians between 0 and 2 pi, or between 0 and 360 degrees if you want. So we look at this here and we have to change it all to sine x's if we're going to solve some sort of quadratic. We have something squared, so that's a good start. This identity here, when you see cos squared x or sine squared x, always remember this identity here, something you may have to use. So we want to replace cos squared by something sine squared. This identity is given to you in the logbook as one of the most common ones. So we can actually rearrange this identity to say this. We can say cos squared x is equal to 1, and when this sine squared x comes over, it's 1 minus sine squared x. Okay? So in effect, we can replace any cos squared x we see by 1 minus sine squared x. So let's rewrite our equation. 2 times 1 minus sine squared x plus 3 sine x minus 3 equal to 0. So 2 times 1 is 2, minus 2 sine squared x plus 3 sine x minus 3 equal to 0. So let's keep the square stuff at the front, minus 2 sine squared x, and we have plus 3 sine x, and now we have minus 3 plus 2, that gives us a minus 1 equal to 0. Now I don't know about you, but I know when I'm solving quadratics I like to make the squared term positive. So I'm going to change all the signs here. That's going to give me 2 sine squared x minus 3 sine x, and then plus 1 equals to 0. Now I'm going to do a substitution. So this is something squared, this is not squared, this is a constant here. So what about this substitution? What about, say, we let y equals to sine of x? What about using this substitution? We can't forget this substitution. That's fine. Now remember, sine squared x is sine x squared, as I explained a couple of minutes ago. So sine squared x is going to be now replaced by y squared. So that's going to be 2y squared. Sine x is, of course, is replaced by y. 3 times y plus 1 equals to 0. Now can we solve this? Yes, we can. 2y and a y equals to 0, and minus 1 and minus 1. The factors of this, minus 1, 2y times minus 1 is minus 2y, minus y, that gives us our minus 3y in the middle. So we see that either 2y is equal to 1 or y is equal to 1, and of course that means y is equal to a half. So I have these two values for y, but of course I have to put them in here. So I know that y is going to either be a half is going to be equal to sine x, or 1 is going to be equal to sine x. So how do I solve for x? Well, now I just get the sine inverse of 1/2 is equal to x, or the sine inverse of 1 is equal to x. And of course we know the sine of 90 is 1, so if you do this in your calculator, look, I'll just do it for you here. So I'm in radians, so shift sine inverse of 1 should be 90 degrees, which is pi over 2. So pi over 2 is equal to x. And what about a half? Well, shift sine inverse, and we'll do a half, 0.5, and it gives me a 6th pi, or pi over 6. So I have these two values. So a small little pause for thought here. Is this all the values we have? So I'm a huge fan of drawing a sketch of what the sine wave looks like between 0 and 2 pi. So remember, we're in the unit circle, so between minus 1 and 1 here, and 0. So the sine wave always starts at 0, 0, and it goes like this. And there's one period of it there at 2 pi, meaning this part in the middle must be pi. Okay? If it was cos, it would have started up at 1 and dropped down and came back up, right? So it would have slightly different. This is definitely the sine of x graph. Now what I want you to see here, and this is really a deeper level of understanding, but you're in honours maths, so I expect you to be here. So sine of x is equal to half, sine of x equal to 1. Where is that graph equal to 1? Well, it looks here, if we come out to 1, the peak of it here is equal to 1. If we track down, that's halfway between 0 and pi, which is pi over 2, which is what we got. So that's where that pi over 2 comes from. What about a half though? It's a positive half, so that's in here. So if we track across there, yeah, we clearly see here that there's our first value, pi over 6, which is what we got. But hang on, there's also a value here, right? Now, notice for 1, between 0 and 2 pi, which is what they asked us to look in between, it only hits the peak of positive 1 once. So this is a good answer here. But it does hit a positive half twice, here and here. Now this graph is symmetrical, so if we come out a pi over 6 there, we come back a pi over 6 here. So it might be a slightly different way than what you were taught, but it's the way I think about it. I mean, I teach physics as well, so I mean, we do a lot with sine waves and cosine waves for electricity and stuff like that. And so, I mean, if you look at this, or you have to know this sine wave graph. I mean, it's big time. It'll help you with these type of sine of 2a's and these type of graphs and solving these problems. So that means if we're at pi over 6 here, let's come back at pi over 6 here. So this is 1 full pi minus a sixth of it back. So what's 1 minus a sixth? Well, that's 5/6. So this value in here is 5/6 of pi, which of course is the same as 5 pi over 6. So the solutions are pi over 6 is a good one for a half. 5 pi over 6 is a good one. And then the other for 1, we have pi over 2. So there were 3 answers. So of course you had to get those 3 answers in between 0 and 2 pi. So hopefully this made sense to you. If not, maybe look back on your textbook or ask a question in the comments and I'll try and help you. That's it.